Why? Because you know your work better than anyone else, yeah? So I want you to go ahead and take a quick peek. Now remember, I don't necessarily need you grading every single little tiny slash mark, even though it should be close, okay? But if you want to, you can try to think of following the flow and whether or not, in general, you have negative slopes, zeros, positive slopes, getting less negative, more positive for that one. Does that make sense? Just a quick check. This one, same dealio. You should have had almost like a horizontal asymptote at the axis and then swooping up or swooping down, depending on your initial condition. These ones didn't technically have you choosing an initial condition. Although some of you guys, as I looked quick, you might have followed the flow just to see what it would have looked like. You should have had a diagonal of flat lines with the flow increasing, or if it was over here, the flow decreasing, there was like an oblique asymptote right about there. This one was parabolic, should have had flat and then negatives and positives. This one should have had a horizontal asymptote at 1, and then increasing, decreasing. That's how the flow would be behaving. Now, this is a big key. You shouldn't have had any slash, any dash, any slope at 0, 0, because 0 over 0 is undefined. I know we say keep going, but that's when we're doing limit. 0 over 0 is an undefined value, so therefore there should have been nothing there. Then you would have had a vertical asymptote at the y-axis, horizontal asymptote at the x-axis, and then swooping, 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 swooping. It was a little awkward, but you guys at least got the idea? Cool. Let's go on to multiple choice because this should be pretty quick. Is there any reason to fudge on this grading? No, you need to see where your weaknesses are, yeah? Here we go. 7, 8, 9, 10, 11, 12. You guys can see E, G, C, A, H, B. Or if you did it the other way, you can look down here. Letters D and F were not used. Sign was not there, and an x cubed was not there. You guys need me to zoom in a little bit? Sorry. There you go. We got it? Next page, matching again. If you went numbers to letters or letters to numbers, however you went. They also gave a quick little hint as far as how they were able to make the match. Do you guys see this diagonal going to plus or minuses, right? And you see like the horizontal vertical asymptotes going to fractions. Parallel horizontally going to in terms of y, parallel vertically going in terms of x. Number 17. I think we did most of this together, but we didn't totally finish it. We did follow the flow, if I remember right. Swoop, there it is. Swoop, there it is. There was that slanty asymptote. This is kind of like the wind pattern with the different countries. Depending on where your point was, it behaved very differently, but that's okay. Equation of a tangent line. That was something we went over in our note packet on Friday, I think, right? And so hopefully we plugged into that y minus y1 equals m times x minus x1. And then using the tangent line, get y by itself, plug in the new x and say, okay, approximately 0.3. That was actually, wasn't the tangent line the bonus on the last test? I finished grading that this weekend. I just need TAs to help me tally up all the points and then record it. And you guys will get it back tomorrow. But tangent lines, they're important and they're sneaky. They sneak up on you. Yeah, Michael? Just for a second? Yeah. Okay, number 18, following the flow. Shoop, shoop. This one was a little awkward, but if you had that point and you've noticed the slopes, it didn't really give any room for moving elsewhere. If it was up here, it would have swooped up. If it was over here, they all would have swooped down. This one was kind of just a slanted line. That might have been a little awkward for you guys. But I gave a hint on letter B. This was the one that I thought was trickiest out of the whole worksheet, which is why in the notes packet on Friday, I went over that other one where I said, even though there's a differential equation, watch the video from Friday if you got stuck, and they talked about a solution to the differential equation, they did not ask you to solve, because this is impossible, bless you, to solve by hand. For you guys, it's impossible to solve a plus or minus one of these diagonal slopes, guys, by hand. So they were not saying to solve the differential equation. So instead of, I even did an arrow on Friday, didn't I? Instead of going this way, integrating, what were you supposed to do? Derive. Instead of integrating, you were supposed to derive. This was very, very, very similar to the one in the notes packet. Very, very, very similar. And then letter C was talking about local extrema. Letter C was talking about local extrema. Now I'm going to go ahead and pause because I didn't do this fully on Friday. I gave a hint about it, but I didn't do it fully on Friday. I want to peek at letter C with you guys just because it is so important. I mean, the tangent lines are so important, but you're going to practice that again when you do your test corrections, sadly, for this last chapter. Tangent lines are important. Differential equations are important, but we're going to definitely practice that as we keep going in this chapter because the whole chapter is integrals applied differential equations. But this whole FRQ thing of finding local extrema, I'm just trying to make me some space here. There we go. The hint I gave on Friday to both period 1 and period 6 was you have to use the second derivative test. Oh, wow, I'm not used to being that on. Look at that, that's perfect. Second derivative test for relative extrema. Okay, that's what you had to use for letter C because you cannot integrate that differential equation and find the max or the min using like critical numbers and all that jazz. So we have to use the second derivative test, and I gave you the hint of you have to look at dy dx and the second derivative. Because the second derivative test says, hold on, does anybody have their forever cards close? Go find me the second derivative test for relative extrema. You guys know what I'm talking about, right? There is the concavity test. Second derivative is positive. The function is concave up. Second derivative is negative. The function is concave down. That's not what I'm talking about. I'm talking about the relative extrema from the second derivative. AJ, do you have the card? Read it out loud. Pause. So I need a critical number, right? Okay, critical numbers. What are they talking about? They're talking about g of 0 equals 0. Yeah? Can you guys look at your differential equation? What's the differential equation for g according to the given at the very beginning? 2y minus 4? Minus 4x. Okay, so if 2y minus 4x is my differential equation, then if I plug in dy dx at the point 0, 0, what's 2 times 0 minus 4 times 0? 0. So what does that mean about the point 0, 0? It's a critical number of g, which is exactly what my card says I need. So do I have a critical number? Yes. Okay, now keep going. No, not if f of x. Careful. Double prime, right? Okay, good. So if f double prime is, what'd you say, less than? Less than. If f double prime is less than, then there's a concave down portion at a critical number, relative max? Yeah. And then if f double prime is greater than 0, relative min. And then if f double prime equals 0, then neither. Now, we're talking about g, not f, but that's okay. We can use differential notation anyway. We have to find the second derivative, which we can totally do, because the second derivative is, well, guys, hold on. You had to do this at least a couple times in the notes and in the worksheet. How do we take the derivative of a derivative? Yeah, so what's the derivative of 2y? dy dx, good. And then the derivative of 4x minus 4. And then can't we plug in dy dx from over here? Cool, so we can go ahead and say this is the same thing as 2 times 2y minus 4x minus 4. So what happens if we plug in the point 0, 0? because we need to know its sign for the second derivative test for relative extrema. Wouldn't we get 0 minus 0 times 2 is 0 minus 4? Which is less than 0. What does that mean about my concavity? Down. And if it's concave down in a critical number, what can I say the function has? Why? Because there's a critical number and the second derivative is negative. Dun, 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 dun. Perfect. Second derivative test. I don't need a sign chart. I don't need before or after. I can't use that on slope fields and differential equations anyway. So if I were you, bless you, I tried to have you guys with a color pen on Friday make a note of this. If they're asking about extrema with a differential equation, you are looking at the second derivative test for relative extrema. You have to look at dy dx at the point, has to be a critical number, and then you're looking at the concavity. I would highlight, I would make a note, because this is a very important AP clue, AP trick, AP strategy. All right, kiddos, thanks for letting me do that. I made a note of it on Friday, but some of you didn't realize quite exactly what I was hinting at. Oh, I was talking about this exact type of problem. But here we go, back to the answer key. Number 19 was B. That one you guys had to do quite a bit of testing. Number 19 was B. Number 20 was C. 21 E. 22 A. If you notice, some of these were closer than others. 23 was E. Which one? C, E, A, and then E. And then we're done. Kiddos, here's what I'm going to do. I'm going to go ahead and post this in Google Classroom. You're going to be turning this in tomorrow. I'm posting this on Google Classroom because if you notice for a lot of these answers, it wasn't just an answer, but also some clues. So if you missed something, I want you to go back through it a little bit tonight and see if there are any questions that you have. Sound good? But why did I have this whole, like you guys, having it ready in class and grading it in class? Because some of you, if there's an answer key available, don't think as hard as if there's not. Does that make sense? Okay. Questions really quickly about the slope field packet. Yeah, Michael.
Can you scroll up?
Oh, yeah, I can. And so, Allie, since it's online, you need to have it attempted and then graded and then bring it tomorrow. Okay. So, you guys know what's going on? I'm going to go ahead and post this just as an attachment to, did you guys see that comment about my reminder? Oh, come on, Google. There you go. So I'm going to go ahead and post it in that comment, in that reminder about the slope field packet being due today. I'm going to attach this answer key so you guys can take a little more time with it. Cool? How many of you guys missed? Well, it's kind of hard. Tonight, I want you guys, when you're looking at the answer key, to give me like a little minus. Count the multiple choice just as -1, and then the free response, count A and B and C and D separately. Sound good? Just a quick little, I know with FRQs the points are very different, but for our purposes, I just want to see how many you missed. And it had to be you missed something on it. Maybe you were like, I was so close on A. Doesn't matter, you still have to count it. That's in our brains being like, ugh, if we get something wrong, we're going to get points off, even if we were close. But you can go ahead and count up, tally up how many you missed, and we'll talk about that tomorrow too. All right, cool kids, let's go back to section 5.2, because I do want to get at least a little bit of work done in 5.2 today. Okay. On Friday, we went ahead and saw, let's see. Yeah, it's okay. We went ahead and saw that, and actually we saw it in the worksheet, first of all, that there are more complicated differential equations than the ones that we saw in 5.1 homework. The ones that we saw in 5.1 homework, I mean, I could open it up, and but I did it on Friday already. All of those ones in 5.1 were in terms of x. All of those differential equations were in terms of x. And so in 5.1 homework, they could have given you something like dy dx is equal to 2x all over x plus 1. I think you guys had one with an e to the x or something like that. But guys, how would you solve this differential equation if they told you to find the particular solution? Or find y equals f of x? Or solve the differential equation? What would you do? Can't integrate quite yet, but Patricia's right. We are trying to go towards integrating. What's the first thing you would have had to do, though? Rewrite it or rearrange it to be dy equals... What would I have to move to the other side? But after I move the dx, am I good to go? I'm totally good to go because I have a function in terms of x dx, and then technically, even though it's just a 1, a function in terms of y dy, go. That's all you have to do. Move dx, and then you're good to go. Everything's in terms of x over here in the sense of the differential equation. But in our worksheet, we were seeing nastier ones. And so Friday, sorry guys. Friday, I gave you a nastier one where the x's and y's were together. You guys played with them in your worksheet as far as matching differential equations, etc., with slope fields or making a slope field out of it. But we have to start dealing with these by hand. And so what we saw on Friday was if we have a differential equation in terms of x and y, to anti-derive or to integrate by hand, I have to get the y's on one side and the x's on the other. And we saw that it's possible. We saw how there could be like a plus or minus situation as far as the absolute value, square rooting a squared. We saw how the c's are going to sometimes now get stuck. But we're not really going further than this right now because that's what section 5.3 is. Section 5.3 is let's just give you whatever nastiness as far as integrating you might be able to handle this year. Now remember, I said the plus or minus is one. There are ones out there that you cannot integrate by hand. You cannot, and you will not be able to at the end of this year either. Actually, even BC can't. However, in section 5.3, they're just going to throw at you all sorts of different ones and all kinds of different stuff might happen. But in section 5.2, we are zeroing in on one specific type of differential equation where the rate is directly proportional to the amount. The rate is directly proportional to the amount with either a positive constant or a negative constant. But the rate is directly proportional to the amount. And this is the basis of exponential growth and decay. And so we saw on Friday that this is a very specific type. Just like the one up above, I had to get the y's on the y side. I had to get this case it's dt because everything's in terms of time with growth and decay. Time is passing and things are growing or things are decaying. We had to move the dt over here. I kept the constant k. This is back from Algebra 1. Directly or inversely, it's by some constant or with some constant. And when I integrated this very particular type, I'm going to get an ln. I undo an ln with an e. We saw exponent rules. When we add exponents, we're multiplying like bases. And then we were like, well, if we're multiplying like bases, well, you know what? E to the c, a constant to a constant, is just a new constant. And so that's how we got to our exponential growth equation. And if k is a negative, it's going to be exponential decay. Technically, we talked about how with this whole absolute value, we can probably do like a plus or minus sort of dealio. But that brings us up to exponential growth and decay. Differential equations where you have the rate directly proportional to an amount, the rate directly proportional to the amount with a negative. But basically, either way, both of them get back to these equations, which is basically letting y sub naught equals c. Because it's really y of t is equal to c e to the kt or negative kt. K can be a positive, k can be a negative. That's what I'm just trying to show there. C's are constant. And so y sub naught is what is typically in that c spot. So here's a few things that you're going to want for today. And the examples that we're going to be doing today and tomorrow and for the homework that's due on Wednesday. There are going to be times where, let's label stuff. Let's label stuff. In this equation, This is going to be your amount after time t. Some people would say the amount remaining, which could be higher or could be lower. It could be growing or it could be decaying. But it's the amount remaining or the number remaining after time has passed. Time has passed, that little y of t is the amount that is currently there. Over here, our c, as you guys can see up here, is going to be our initial amount. Which is the same thing as y of 0 or y sub 0. Because if you were to plug in 0 to this specific growth equation, and 0 power is 1, and so c would equal the y of 0. So that's our initial amount. K in some way, shapes, or forms. K can be our rate. We'll say our rate constant. That's an awkward way of saying it. There are other ways of saying it as well. In chem, you usually memorize a value for K to use when doubling or to use for half-life. But we're going to deal with it a little bit more mathematically. And T is how much time has passed. There are going to be times where it's going to be helpful to make a ratio of the final with the initial amounts. So we could do y of t over y sub naught is equal to, we could basically divide the y sub naught to the other side, and we would get our e to the kt. You can also think of it as y of t over c. But this is when they're talking about some sort of ratio, some sort of percentage. So for instance, if they were to say something like doubling or doubles, we could say that y of t over y sub naught, what was and what is equal to 2 or 200%. If it cuts in half or a third or a fourth, we would make that ratio, what is to what was. So we can kind of rearrange the equation in the sense of making a ratio ourselves and setting it equal to the other amount. Once again, if the AP made us like really deal with this, we would probably make this into a forever card, probably a couple forever cards. But since it's just for this section, I'm just showing you kind of like this is our little cheat page, and then we're going to use it. So doubling y of t is equal to twice the initial. Half-life y of t. And we could even actually say doubles at or by t equals b. Then I could say y of b is equal to 2 times y sub naught. If it's a half-life at time b, I could say y of b is equal to 1/2. There are other ways of writing it besides the ratio equaling 2 or the ratio equaling 1/2. Doubling will always be growth because it's growing. Half-life will always be decay because the old amount has become half of what it is. Radioactive elements, we talk about half-life. Carbon-14, we talk about, or could talk about half-life. Just some examples of decay that is commonly measured in science. But all of that kind of brings us up to an example. Now, technically the beginning of, sorry, you guys don't have a handout because we actually have a nice section for it. The very beginning of your guys' section 5.2 might not necessarily go into word problems yet. We're kind of used to math books and how word problems are usually at the end. So let me peek really quickly at your section 5.2. I know you guys are grading your slope field or going over the answer key to your slope field packet. But if you were to look at the beginning of homework, just because I'm always a proponent of not leaving homework till the night before it's due, even though this one is due Wednesday by the end of the day so that you guys can work in groups a little bit on questions. You definitely don't want to leave the whole homework for that. And you want to be working some on section 5.3. But if you realize the beginning of your homework actually just says to do what? Oh, well, not differentiate, careful. The derivative's already there. So instead you're solving. Now, in some of these, it's going to be pretty basic. Like these two are just in terms of x. So guys, what are we going to do? We're just going to multiply the dx's to the other side and integrate, right? But what's the problem with these ones? If you multiply by dx, what's true? Ooh, right? So let's peek really quickly at this example that I have. Because if we were just to multiply by dx like we've been doing, can we, now some of you wouldn't put your parentheses and you would be in some big hot water right away. You'd be in some trouble right away. But if you put your parentheses, because 4 minus y is grouped when you multiply, does this belong with that? No. So the only way to deal with it is to move it to the other side. The whole thing. We have no options on this one. And then to integrate. And some of you might realize over here it's not going to be a big deal, but over here, why am I writing u equals 4 minus y? Because I need to use an ln, but I can't forget my u sub. And so the beginning of homework is just kind of having us deal with these differential equations where we're going to be getting ln's, kind of getting us ready for this exponential growth and decay, because in all of these ones, when we solve, we're going to have to get in some exponentially things. A negative times an arbitrary constant is still a negative. But all of these exponential comes out, because as soon as you get an ln around y's, you're going to need an e. Now you guys, I don't know why it's not very noisy outside, because people should totally be coming through the hallways right about now. But if I were you, I would start playing with just the beginning differential equations in section 5.2, and tomorrow we'll play with word problems. Sounds good? Get out of here. There's somebody in the hallway. Man, everybody's going slow today. And hopefully I'll be coughing less. Bye, guys.